this one is written as summation over xt, which is the hidden variable right now. It's a marginalized variable. Xt plus 1 given xt, e1 to t, and xt given e1 to t. So, if I happen to know this, then I can write it this way. Right? Now, xt plus 1 given xt and e1 to t is nothing but xt plus 1 given just xt. Right? Xt plus 1 depends only, so because, again, look at the, so xt plus 1 given this as well as all these guys is just this given this, because these guys are de-separated from this guy given this guy. Remember the old Bayes network terminology, de-separation. Okay? So, all I need now is this. But this is just a recursive procedure now. To get xt plus 1 given e1 to t plus 1, I just need xt given e1 to t. So then I recurse myself on this now. Finally, at some point of time, I will get to x0 given nothing, which is known in the, my procedure in the thing, and so I just recursion comes along. Okay, so again, there's no, there's no magic here. Essentially, all I'm saying is, if you looked at this as a general Bayes network, you would have had this huge big Bayes network, and you would have just used some exact inference method. But really, because of the repetitive structure, you can roll up behind you, unroll front of you, roll up behind you, unroll front of you. That's what you're doing. So this is my flawed red carpet analogy. I'm walking on my little red carpet, which is only 2 steps long. So when I make one step, I lift my leg, roll it up, and then somehow, jump up and push it forward. And then I keep going. I'll never have to get down. Okay? So that's more or less what's happening in the recursive procedure. Okay? And this is now, what's interesting is, this is going to take a constant space, because it is only going to have to remember the current state's distribution. And it doesn't matter how long in the future you're going to go into. Because at every point, you remember my previous guy's distribution, I compute my distribution, then I go forward, I use this distribution to compute this distribution. So every time you're only remembering x distribution over xt, given the evidence. And the distribution size of xt depends only on the domain of xt, not on how long, or how large number t is. Do you understand what I'm saying? Because the state variable, the state of the state of the system is the same, has the same number of variables. It's just that they are indexed with respect to time t1, t2, etc. It's not that at the t20 you have more state variables than you had in t1. It's just you had different values for the same state variables. So the distribution itself will have the same size table. So it takes constant space. Okay, so as it doesn't look very impressive, but it's a very impressive thing, and it's possible only because of the structure of the Bayes network. Okay, structure of the dynamic Bayes network. Okay, so the example that's being done here, essentially, I mean, of course, the way the recursion actually works is it would be trying to compute this when it would be trying to compute this when it would have recurse down here, and once you have these numbers, then the recursion will complete. Okay, but it will be better for us to understand in the forward way. Okay, so you have the distribution of range 0, which is 0.5, 0.5. Okay, using just the transition function of range 0 to range 1, I compute range 1's distribution to be 0.5, 0.5. Using the fact that umbrella is true and the Bayes rule, I recompute this to be 0.81, 0.182. Okay? This is happening because you use the Bayes rule. So because what happened from here to here are 2 steps. The first step was it's alpha. I mean, so this probability is proportional to, so A given B is proportional to, I mean, A given B can be written in terms of B given A using Bayes rule. Okay, so all I'm saying here is A given B is alpha times B given A, where B is E1 to T and E1 to T and Et plus 1 given xt plus 1. Okay, that is then written using chain rule into these two parts. So it was actually using Bayes' rule here. Okay, and that Bayes' rule, basically when you have the evidence, that Bayes' rule will basically tell you this will transfer to 0.81, 0.8. So you expect that it's like half likely to be raining, half likely not to be raining, but then this guy is wearing, bringing in an umbrella. So using the Bayes' rule, which is basically abductive inference from a logic point of view, from the evidence to the causes, okay, you change your distribution for rain to be more inconsistent with the evidence. So it's now in this case 0.818 and 0.18. Now at this point I use this and this to compute this. So as far as I'm concerned, I can cut these off. I now have a little Bayes network just from here to here, where the prior for rain 1 now is 0.818, 0.182, which is then taken over the transition function here, and it becomes 0.627, 0.373. Notice, essentially, if you don't have any evidence, uncertainty keeps coming in. Even though you knew it was pretty much raining today, this day, okay, because of the transition that says raining doesn't mean raining tomorrow, and not raining doesn't mean not raining tomorrow, everything kind of over a long period becomes equalized. Actually, it reaches a steady state probability. It's not always equal to uniform. It will be the Markov chain steady state probabilities, which you actually used in page rank computation, etc. Okay, stationary distribution. Okay, so in this case, so basically that's the mixing distribution, and then that will be normally much less informative than what you would know based on the actual evidence. Okay, so based on this, you really just the transition, you thought it would be 0.627, 0.373, and then using the fact that there is an umbrella again the next day, you change this to 0.883, 0.117, which is the posterior for second day's rain. Okay, and if you are now asking for prediction, rain 3 prediction, then I just need to take this over the transition function without any evidence to rain 3. If I want for rain 4, I take it once more to rain 4. And as I do that, I'm essentially mixing. This is called mixing of the Markov chain, so it will then reach a steady state distribution. And that might typically not be as indicative of the true state as you would know if you actually had evidence of what is actually happening. Okay, in this particular case, it will be again 0.5, 0.5, because essentially you're starting with 0.5, 0.5, and if your model is such that, I think in this case it will be 0.5, 0.5. It's the mixing distribution depends on, doesn't depend on the prior, it depends on the transition function. Okay, so that's an example of, so we looked at how dynamic Bayes networks are templated representations. We also looked at how certain kinds of Bayes network inference are more important in dynamic Bayes networks than just normal Bayes networks. And then we looked at how at least one case, the exact inference, can be changed, tailored to exploit the structure of the network. So this is the kind of thing I meant at the end of last class, where I said rather than just convert the PRM to an underlying Bayes network, you want to somehow do better. And there are different ways of doing better. One is, at least as I was saying there, at least don't ground all parts of the objects. If only certain objects are relevant, only ground the network corresponding to that. But it will be even better if somehow you can do lifted reasoning without actually talking at the ground level. Okay, I didn't get to talk about how to do those there, but analogously here we talked about how for a templated representation for dynamic Bayes network, exact computation can be changed. And if I have a few more minutes some other time, I will tell you how the likelihood weighting is changed to particle filtering. Okay, that's it.